Hi everyone, let's get started. Hi. Hello? Is this working? Can people hear me?
I mean, we can hear you, but probably people there cannot.
Okay, sorry. Let me try to fix this mic. Okay, can folks hear me? Great. Okay, so just before we start, an announcement. I just posted the homework 3 right before the lecture. It's about vectorization. Should be much shorter than the previous one. But please take a look. And yeah. Just I guess looking forward, there's 2 more homeworks after this one. The next ones after that are MPI, which is distributed memory, and GPU. And they will both be still on particle simulation. So we'll be going back to it. Right. So today we are doing data parallel algorithms. Okay. So like I said in one of the previous lectures, single instruction multiple data or SIMD machines run on one instruction stream. So you give one instruction like add or subtract or multiply, and all of the compute units do the same instruction. Here are your units, and they each have some value inside, and they all do the same operation on the data, which is different from what we just did in the homework, which is like thread parallelism. So all the threads can do different stuff. And the processing units communicate through some shared memory. Data parallelism is the programming paradigm where everybody is doing the same operation on multiple values, often array elements, and you can also do collective operations like reduce, broadcast, and scan. And a lot of parallel programming models use some kind of data parallelism. For example, in pretty much all modern machines or multi-cores, there are SIMD units. These are in the form of vector registers. And previously, there were supercomputers that were just based on SIMD paradigm. And CUDA and GPUs are pretty much all SIMD. And there's MapReduce, which uses two basic primitives, map and reduce, which are also SIMD instructions, and MPI collectives, which we'll learn more details about those later, but those include things like doing the same operation for everyone, like reduce or broadcast. Yeah, this is what it looks like. You have some data and you have the processing units, and then one instruction for all of them. So the most simple SIMD type operations are called unary operators. And unary operators, you take in an array and you apply the same function to all of the elements in an array, and you just have one. So for example, squaring. So here, 3 squared is 9, 1 squared is 1, and so on all the way down. And everybody, you just apply and multiply to the same, to every element in this array, and then you get this result. Slightly more interesting is binary operators, which is you have 2 arrays, here A and B, and we apply some operation to every pairwise in A and B. So for example, here, we would have minus, so A0 minus B0 is 3, 3 minus 0 is 3, 1 minus 1 is 0, and so on all the way down the line. And notice that all of these are independent from each other. None of these elements conflict because they're just doing like separate subtractions. And you would do those for any other operation like multiply, add, and so on. Previously, I was talking about broadcast. So broadcast, you pick one single value and you fill that value into all elements, into all slots in an array. So in this top example, your element is 3. And if you broadcast 3 into vector B, then all of the elements become 3. Broadcast is useful when you want to do things like one of these classic operations that you might want to do is called Saxby or Daxby. And what that is, S and D are for single and double precision. Axp is just AX plus Y over there. So A is a scalar, X and Y are vectors, and you would just multiply A into all of the elements of X and add them with Y, like here, 2 times 3 is 6, plus 1 gives you 7, and so on. And implicitly, you would broadcast 2 into some array to do the multiplication here. You can also do assignment in a vectorized or in a SIMD way if the arrays are the same shape. Like, for example, you have array A, which is a double with 5 elements, or an array of doubles with 5 doubles, and then you have some B, and you fill it in with some values, and then you can set A equal to B because they match in terms of the shape. You can also set a stride, so your copy doesn't necessarily have to be contiguous in memory. On this left side, we have the way to read this notation. 0 through 4 is the elements that you want to copy, and this 2 is the stride 2, so this is copying every other element into A from B. And then C, if you had a matrix, a 5 by 5 matrix, you can also copy arbitrary rows and columns of C into A, which is a vector of length 5. So this C star and 3 would copy this fourth column, I guess, because we're 0 indexing into A. And C, if you store C in row major, those elements are not contiguous. Okay. Another primitive that we often use in SIMD is called scatter gather. So gather is you have some array, this is your data, and you give it an indexing vector. So here 7, 12, 8, and 2. And those are the indices of the elements that are going to go into your output. So element 7 is 9, or the element at the 7th index is 9. The element at the 12th index is 3. The element at the 8th index is 5, and the second one is 3. So when you do this gather, you give it this indexing vector and the total array, and then those populate this subarray. And then scatter is the other way around. You give an indexing vector going out, and then you put those values in this order into those indices that you specified. And we often use this in sparse linear algebra, sorting algorithms, FFT, and so on. Sorry, yes.
What's the difference between broadcasting a value into like a vector or assigning a value to a vector?
Let me go back. So here we're just doing vector assignment in this example.
I see. Okay. That makes
So,
sense.
yeah, so A and B are both vectors here, but in this example, A is a scalar and we assign B equal to A. And since the shapes don't match because B is a vector, then this is a broadcast.
That makes sense.
You can also introduce a mask for your operations. So here we have these arrays A and B, and our operation is A plus B, A equals A plus B, and we give this bit mask M, and 1 is the values that we actually want to compute, and then for 0 we just pass those through. So here 3 minus 0 is 3, or sorry, plus 3 plus 0 is 3, 2 plus 1 would be 3, but this is set to 0, so we would just do nothing. And so on for the rest of them. Okay. We can also, one of the main things, like in my view, one of the more interesting things to do in data parallelism is things like reduce or sum. So if you have, this is a common thing that you might want to do, you have an array and you want to collapse it down into a scalar, where the scalar is the sum of everything under some associative operation. So here it's just addition, and you can also do it for dot products, because if you did, yeah, that is just summing all of x times y. So if you did element-wise x and y, and then you multiply them all, then you would get the dot product. The most fundamental thing in data parallel programming is doing scans. So scan takes as input an array. You have x of 0 up through x minus 1, n minus 1, so that's n elements. And then you want to output an array y. Y is the same shape as n, or y is the same shape as x. And for every element of y, the first one is just set to the first value of x, and then the rest of them is the cumulative sum up until that point. So y of k is recursively defined, is equal to x sub k plus y sub k minus 1, where y sub k minus 1 is the sum of all the stuff that came before that. Yeah, so you can do the scan for any associative operation as well. So here, this example is for addition. 3, you start at 3 for B. 3 plus 1 is 4. 4 plus 1 is 5, and then you keep going like that. You can also do it not necessarily for just addition, like here's an example with max. So max, the max up until this point is 3, and then after that you see 4, the max after that is 4. And there's two variants of scan. Inclusive is the one that we just saw, which is that you include x sub x when you compute y sub x. So you just include the point that you're currently at. And another variation is called exclusive scan, where you don't include x sub x when you're at y sub x. So you're just everything before that. So this is exclusive scan. You put the identity in the first position. And then now the second here, you just include up to, sorry, this is the inclusive one. And then here, you would just put the first element. And then here is 4 and so on. So you can see that you can easily get the inclusive one. If you have an algorithm for exclusive scan, you can easily solve inclusive scan by just adding the input in element wise. But for the other way, it's not so obvious how to transfer. Yeah, so you can go exclusive to inclusive easily, but to go from inclusive to exclusive, the easiest way is to use an inverse operator if you have it. So in this case, you do have it. It's an addition, so you can just subtract. But that doesn't always work. Like for max, there's no inverse. Yeah. Does that make sense so far?
It doesn't really matter, but like before, like at the start, you do the identity. What would be like the identity for max?
Maybe negative infinity. Yeah, it's a good point. Wait. Yeah, that would work. Good question. So when we want to analyze these, the performance model that we use is pretty much the same as the workspan model that we were talking about last time. Usually in SIMD, like the picture of the machine looks a little bit different. You have many tiny processors, and each processor does the same instruction. And with the bit mask, you can turn off some processors for some instructions, but each one has a tiny memory where you load like your two operands, and then you have some interconnect between them. Like in the previous model, we assume that we have some unbounded number of processors and that we're not calculating control overhead, and we're also not counting communication or cache misses. Like in workspan, we weren't counting cache misses. That was a separate model. And in this case, again, we're going to count the complexity as the span, which is the time on infinitely many processors. So we were talking about reduction earlier. You can do a reduction in log n span by doing this tree-like summation. So first you would do all pairs, and then you just recurse down through all the like the previous results that you've done. And in the end, this takes log n. This tree has log n height, and you would get the total reduction at the end. And this takes advantage of associativity in your operator. Can we do better? So if we have this function, we're doing it on f sub 1 up to f sub n. You have n input variables. Sorry, let's just say one output variable. How fast can we do it in parallel? In this case, you have to take log n steps because if you have binary operations, then after one time step, you can only have computed on 2 elements. And then by induction, after k units, you can at most have computed on 2 to the k inputs, and you started with n inputs, so you had to do at least log n phases. And you can use that reduction algorithm to, going back to matrix multiply, you can do matrix multiply in log n span. So matrix multiply, you can, if you have infinitely many processors, you can think of it as a cube. So if you just put each point in the cube is ijk, where ijk was the index into the matrix, then each one of those points, you can think of it, you can do a multiply. Those are the multiplications that you have to do. And then you need to reduce them because you had n cubed multiplies, but you want to have n squared output. And so now you have to do a reduction along k to get into ij, and you can do the reduction in log n using just the same tree-like summation that we just did. So yeah, so this multiplication, if you had infinitely many processors, would be just 1 in your span, and then the the summation is log n, but you can do all of those in parallel. And then that's it. The multiplication is done. Okay. Does that make sense? All right. So the rest of this talk, or rest of this lecture, is pretty much about scan, because I think scan is the most interesting data parallel algorithm. Can we parallelize it? So serial scan takes n-1 operations, because you can implement the recursion directly that we just had. You just make this for loop, and this is inclusive scan. So y sub I is y-1 plus x sub I. And at first it looks challenging to do the parallelization because the ith iteration depends on the previous iteration. So it seems like you would need to have a valid value for this. I mean, you do need to have a valid value for this before you compute y sub I. Okay. So one thing that we can do, an initial step, a very easy one, is try to parallelize over the values. So we have an algorithm to do reduction. We can do that algorithm on every element that we have. And then that would give us the scan result. Like we would just run the tree over all elements before us. And so like, yeah. And that would give us span log n because each of them are independent and the height of the longest one is log n. But the work is n squared because it takes n work, or it takes k work for the kth position to do it. And if you sum up I up to n, then that gives you basically n squared. And that's not ideal because we want work efficient algorithms, and work efficient means that if you have a parallel algorithm, you do no more than a constant factor of work over the best serial algorithm that you have for that problem. So we had a serial algorithm which takes exactly n steps, and now this is n squared. So the span is good, but the work is not ideal, so we want to improve. One of the older algorithms for prefix sum is from Hillis and Steele from this paper in 1986. And their algorithm is these two loops. The outer one goes from 0 up to log n, and the inner one goes from 0 up to n-1. And the way it works is that if you are less than 2 to the I, where I is the index in the outer loop, then you just take the value from the previous step. Otherwise, you do some addition. And the addition is based on your index j and j minus 2 to the I, where 2 to the I is like the power of 2 at your current iteration. And this is the, I guess like it's kind of like a circuit diagram for how this works. So like in your first phase, you do just the pairwise additions. And you do the pairwise additions and you pass through every other one, and then every other one that isn't passed through gets a sum.
I'm sorry, I'm a bit confused. Like, what are the two? There's like a subscript and a superscript. Is that what? Is that? That's not an exponent. I'm assuming that's not an exponent.
That's not an exponent. That's the value in the i+1 iteration, like in the next step.
Okay, so the value of xj in the i+1 iteration.
Yes.
Okay.
In the i+1. The top one is the iteration of the outer loop, and the j is just like the index in the array space.
Okay, yeah.
Yeah, so like let's just look at one example. So for this one, for the first one, we just clearly have to pass it through all the way down. And for the second one, we can just do this pairwise addition with 0 and 1, and then that is finished. For the third one, it gets passed through in the first step, and then in the second step, we already have the addition of the previous, in some sense, like the previous power of 2.
Yeah.
And then we add that, and so on. Like basically at every phase, you add it. You add like the next lowest power of 2 in if you're not finished yet, and by the end, then you finish them all because you've done all the powers of 2. That makes sense? What is the work in the span?
Well, the work is log
n. Good. Yes. The work is n log n. You can say like the outer one is log n, the inner one is n. So you multiply them, that's n log n. And the total span is log n because the outer one has log n steps, but you can do all the inner ones in parallel. So that's span 1. So this is an improvement over what we just had. The work is now n log n, and the span is log n, but it's still not work efficient because we had a linear algorithm. So there is a work efficient algorithm for parallel prefix. And the high level idea, I think this is really cool actually. So I'll try to explain it. The high level idea is that we have this algorithm to do reduction, doing this pairwise like tree-like summation all the way up. And in some sense, like along the way, we're computing partial sums. Like on the way up, we're computing at the powers of 2, the partial sums. But that doesn't give us everything because we need n and we had log n answers. And so we save those in some algorithm called an upsweep. And then you propagate those down in something called a downsweep to compute the total prefix. And the way that the downsweep works is basically you do the sums down the prefix sum tree. So this is the way up. So we have this vector. This is computing exclusive scan, but it doesn't matter because, like I said, you can easily generate inclusive from exclusive. So this is just your tree-like summation on the way up. Like you do this pair first, these pairs, and then you do 4 plus 7 is 11. So this is your tree, and this is your tree. Like this just flipped the other way. Okay, so but like now we have some answers like 4, 11, 14 is done. Or sorry, 25 is done. And 14, 5 is actually the result of these two. And 9 is the result of these two, and then we got 14, which is the sum of 9 and 5. So 14 is like these 4, and 11 was these 4. So we do have some answers, and we don't have a lot of final answers, but we have some sums of some ranges. And basically the way it works in the downsweep is that we flip the tree, and for exclusive scan, you put the identity in the end, and then you think of this as like a top-down tree, then you push the value from the parent into the left, and then you do the parent plus the left child answer from the upsweep in the right child. So here, you push 0 down to the left, and 0 plus, you get 11, because 11 is the left child from the upsweep, and 0, you push 0 down that way, and 4, because 0 plus 4 was the left child. And if you keep going all the way down, then you compute the scan for the entire thing. Yeah, and this is the algorithm, like I just said. You set the left child equal to the parent, and you set the right child equal to the parent plus left child from the up scan. Okay. This is actually, I think it's not obvious at all that this works. And this is just another example. You do this pairwise tree, just pairs, and then pairs for like a bigger step, and so on. And then this is how you get the reduction. And if you want to do the inclusive scan, it's not, the illustration isn't as easy because in the other one, we just flip the tree the other way. But this one, you have to slightly change the offset of the tree. Like here, you don't put 0, you don't put the identity in the end, for example. You keep the answer because you already computed the full reduction, and then you just shift the tree over a little bit. But you still kind of do the same algorithm. And then again, with a similar downsweep in the same complexity, you can get the full inclusive scan. Okay. And this is the pseudocode for up and down. And this is the picture of the circuit diagram. Okay, what is the work in the span? Yes, good. The work is n, and the span is log n. And the analysis is just from these recurrences. I guess these are for both, like either the upsweep or the downsweep, and then you would just multiply them by 2 to get the other one. So we gave up, the span is exactly 2 log n. So we gave up a constant factor in the span compared to Hillis-Steele, because that was exactly log n. But then we reduced the work by a factor of log n. And the work is also 2n. So it's a tiny bit more than the serial algorithm, but it is just the constant factor more. Yeah, and it turns out that you can pretty much do a huge class of algorithms just based on scan or like scan-like ideas. So I just want to, the rest of this is pretty much examples about how you would do that. Does that make sense? So a few things you can do. You can add n-bit integers in log n time. You can evaluate polynomials. You can do recurrences. Radix sort is based on parallel scan. You can do applications in image segmentation. You can traverse linked lists, like you can count the rank of your elements in linked lists, and there's a lot of other ones. And I won't talk about all of them, but I will go through a few of these. So one really straightforward one that we might want to do, but that is actually useful in a lot of applications is called filter. And filter is just given a sequence of elements A, so this is just an elements, and a Boolean flag array B. And you want to basically compact the elements of A according to this flag. Like you only want to keep the elements that saw true, and you want to make the array only the size of, or yeah, you want to get your result array only the size of the number of trues that you had. And you want to keep the ordering. How would you do this with prefix sum? Maybe I just can give a hint. You can think about doing prefix sum on the Boolean array.
You that like you'll get like one or maybe like 1, 1, 2, 3, 3, and then you can like do a flexible. If you do like maybe you do a scatter on that, but that wouldn't really make sense. And not a scatter, I gather.
You basically want to do a gather on that. So like you said, if you translate this into a bit array and you do a prefix sum, and like you said, you get 0, 1, 1. I guess this is the exclusive sum. Yeah. No, inclusive sum.
Yeah, it's exclusive, right? You're starting with 0. But that
Oh yeah, this
that
is
makes
exclusive.
sense.
Yeah. This is an exclusive sum. And in the end, you get the total number, which is 3. And like you said, you get 0, 1, and 2. And these 0, 1, and 2 are the positions of the elements. So you can find these positions by you do a parallel 4 over the entire thing, and you look at the places where it changes. And where it changes, the one on the right is the position of the element, the corresponding element with the same index. Does that make sense? And I guess this is what I said, like you just look for the positions where they differ, and where they differ, you use the index to tell you where to put the element from A into the output. And so the prefix sum in B tells you the position in the filtered array, and the parallel 4 tells you the position from A in the
And
output.
this is better than just like, because you already have the sum. Because if you just wanted to like parallel 4 over array B, you wouldn't necessarily know the sum until like the end, or you wouldn't even know the sum necessarily.
Yeah, if you just did a parallel 4 over A, like you can tell which ones you're trying to filter out, but you don't know where they would go in the output array.
Yes.
Like you want to compact them to the left.
Yeah.
Because you can easily copy them and just like zero out the ones that you're not copying.
Or if you do like a parallel 4 over like A and B, but then you wouldn't know like the sum, you wouldn't know how much you have to like fill in.
Yeah, exactly. Like you wouldn't know how big the output needs to be, and you wouldn't know where they would go in the output.
Can you elaborate exactly what you mean by you wouldn't know where they would go and something like that?
I think you would know where they go, right? If you do a parallel 4, you'd still have the index to like put it in there, right?
I mean, if you just
So if you do, you're saying like if you didn't do prefix sum on B,
just parallel.
just parallel 4 on A, like you would only have the index originally in A, but you want to map the index in A to some index in A prime. Does that answer your question?
Oh, yeah.
Yeah, like you can easily copy A into an equally sized array and then zero out the ones you didn't want, but you want them all packed to the left.
doing each thread will match with the secret and put value to the position that it matches. So they will be checking that is in.
I see. So you're saying like one way that you can generate the flag array is with atomic fetch add?
So I don't need to generate B flags. So I can just have global atomic to indicate value to put the index to insert, and I do atomic fetch add for each thread. So they will have they will guess which position actually inserted.
Sorry, I don't think I understood the question. So basically, instead of doing the Boolean array of the things to filter on, you're saying you keep an array of values or one value?
So one atomic value to indicate which position to insert into, and I parallel those with both array A and B. And if I see a true in B, then I atomically fetch add the positions that I need to insert into.
I see.
As I
That would work. If you want to keep the order, the original order from A, then you need to do something like this. If you do what you said, then you may change the order of the elements.
Yeah.
And depending on your application, like you may be fine to change the order, or if you wanted to keep, depending on if you need to keep them in order or not. So yeah, and then the way that you generate this Boolean array is you can, like the pre-step that you would do to generate the Boolean array, you can filter on some condition, like all values for which they're even, for example, or something like that. Okay. Yeah, so another one is doing radix sort. So this is just a serial algorithm for radix sort. Suppose you have some array up there, that's their starting array 4, 7, 2, 6, 3, 5, 1, 0. And the way it works is that you start from the lowest bit and you go up to the highest bit and you sort first on the least significant bit. So like I said, doesn't matter what's in the upper two, all things that are 0 are going to be less than all things that are 1 in position 0. And they're not going to be sorted like after one phase, they're just going to be bucketed. So here, these are evens. So 4, 6, 2, 0 are kept in the same order. They move to the left, and all the odds move to the right. And then we do the same thing again, but now on bit 1 rather than bit 0. So we bucket them again, and we move the things with bit 0, bit 1 equal to 0, which is blue, to the left, and pink goes to the right. And again, blue goes to the left. Now blue is 0 axis, and then pink goes to the right. And in the end, they're sorted. Does it make sense why this works? So that's how you do it in serial. And if you want to do it in parallel, it turns out that pretty much the way you do it is very based on scan. And the high level idea is the same, like you still go bit by bit, but now each step is more complicated. So let's just start with the 0th bit. So we make these two flag arrays. One, let's say, yeah, so we make for odds and we make for evens, because that's just we start from the 0th least significant bit. So that's just going to divide us into odd and even, and we set this array 1 and 1. And then we do a prefix sum on the evens, and that's going to tell us the positions of the evens in the output array. So this is like a similar trick that we just did in the filter, but now, yeah, this is for evens. And yeah, so we basically are doing a filter, and we're filtering on whether it's even or not, because we are trying to put those in the first half or the first kth, where kth is the number of evens you have. And so then you also, in addition to the prefix sum, you also get the total number of evens that you have. That's just the end of here. It was exclusive sum, but like you can just get at the end the total reduction as well. Yeah. So okay, so you also have the total number of evens as well, and you have then you make an index array where index array is just all the numbers 0 up through n-1, and we want to. So now first we found the positions for the evens and where the even elements are going to go, and now we want to find the position for the odd elements. And so the way we do that is we take the total number of evens, because we know the odds have to start after that. And then we just add the number of evens into the index. And the ones that are odd, like that is the position of them in the indexed array. So we're only going to use the one, like, there's garbage values for the ones that aren't odd, but the ones that are odd, we'll use these indices to copy them. And yeah, so then we use those, then we get some positions array, and we get the positions array based on masked assignment. So if they were even, then we just directly use index. If they are odd, then we use the ones from odd positions, and we do a scattered, index scattered. And that is, yeah, that's how you do one of the bits in parallel radix. And then you would just repeat this whole thing for bit 1 and bit 2 and so on. But the main thing to notice is that this relied on that we were able to do parallel prefix. Well, we did prefix, and if it wasn't parallel, then it would just be n at each step. But now the span for this entire thing is log n. Okay. Yeah, so this is the pseudocode of what I just said. What is the work in the span?
And it's log n,
Or
or
b log n.
the size of, yeah, b log n. Right.
Well, that's the work. Yes, exactly. Yeah. So the work is b times n, because you have b iterations of the outer loop and n iterations, or each step inside, there's a constant number of steps inside the loop, and each one of those takes at most n. I think they all take like n. So the work is b times n, and then the span, the most complicated thing was the prefix. There's a couple like just parallel element-wise adds, but those are span like 1. So the total span of each iteration is order log n times b is b log n. Does that make sense? It's a little complicated. Okay. So another way that you can use parallel prefix is in adding n-bit integers. So we have 2 n-bit binary numbers, a and b, and those are just the bits like a n sub 1 up until a sub 0, and b is the same. And you have s equals a plus b, and it has one more bit than a and b because you might have a carryover. And then you have some side carry bit array starting for n minus 1, and we're going to, this is for convenience, -1, but you can just kind of think of it as like c up to 0 up to c minus n, where this is like whether you had a carry from the summation of a and b. Okay. And in serial, if you were just to add this in serial, you would just add like right to left, and you would just compute the carry bits one by one, and you would use that carry bit in the next bit. So this is just for, yeah, c minus 1 is 0 is just to make the iterations work out. You can, like I said, you compute right to left, and the sum is a of I XOR of b of I XOR of ci minus 1, where this is the carry bit, 1 to the left, 1 to the right. And carry bit is a of I XOR b of I and the carry bit from the previous iteration. I guess, or, yeah, and then you have an or, and if both of these are set, then you're going to get a carry bit no matter what happened in the previous carry bit. So that's how you do it in serial. This is the most straightforward way. But again, now you have this dependency on ci minus 1. Like, if you just went right to left, you would need to compute the previous carry to compute the next one, because the next one depends on not just a and b, but also the result of what happened in the previous step. Okay. So yeah, and this is just an example. A is 22, so this is the binary representation of 22. B is 29, and if you add them, this is the carry bit, so 0 XOR 1, 0, and then there's no carry from the previous one. 1 XOR 0, 0, 1 and 1. This is actually 1, I think. Yeah, because you should get 1 carry from 1 and 1.
There it is.
Oh yeah, sorry. So it is actually 0. Because this one is this. Yes, okay, because it's like this. Yes, good. Yeah, okay, I see. Okay, and then yep, you get the summation, but you needed the previous carry bit to compute into the next one. Okay. And again, if you do it like this, the span is order n, because yeah, the span is order n because you're going one by one. So we want to come up with an algorithm to compute all of the carry bits in log n span.
Would you, okay, I'm just spitballing, but like, you like scan over like A and B and like just like have a like either 0 or 1 and you like add and then like not exactly this because not exactly this won't work, but like you add and like in the scan it would like only be 0 or 1, but like when there's a 1 you know that there's a carry, so you just keep scanning. Like, okay, so for here it would be like 0, 1. Okay, that wouldn't exactly work. But like somewhere like where it switches, like in the previous thing, like, you know, like when it switches from 1 to a 0, at that point, there'll be a carry bit. You know, there's gonna be a carry bit in that index or something. Maybe something like that. I'm not exactly sure.
Yeah, so are you saying like for sure you can compute this part in parallel, like AX or BI? Yeah, AX or B,
course,
AX or B. That is, you can easily parallelize that, and you can also easily parallelize this one.
Yeah,
Like,
yeah. I was wondering how to like calculate the carry bits, or like do a scan. I was like thinking of doing a scan over A and B to calculate the carry bits. But,
And you can also say like this one, if this is true, like you can calculate some of the carry bits. Like this carry bit will definitely be 1 if this part is true.
Yeah.
So you can compute some of them, but not all of them. If you just have A and B.
Or no, well, I was thinking of. I was like spitballing like an algorithm how you calculate all of them over with like a scan over A and B. But I don't have like a thing that works.
That's okay, I can tell you how it works. It's actually, I think it's hard. Like it took me a while to understand. Even with the answer, like it took me a while to understand how it works. So I will tell you how to do it. So yeah, so that's just the way to compute the carry bit that we had on the previous slide, A XOR B, and with the carry bit, you have 2 cases. This one and this one. In this case, you set the carry bit no matter what. In this case, it depends on the previous carry bit. And the high level idea is that you split when you set the carry bit into 2 cases, regardless. So there's the 2 cases, like one, you set it regardless of whether or not you have carry in, and one, you set it only if you have the carry in. And so the first one, they call it the generate bit, which is just the right part of that. Like this column will definitely give you carry out no matter what the carry in was, just A and B. The second part is propagate, which is only if you have a carry in will you get a carry out. So that's A or B. X or? Should be A, X or B. Yeah. And so you can compute these 2. Yeah, you can just compute those 2 parts in parallel, like I just said. The high level idea is basically to unwind the recursion. So we can define each carry-in in terms of P and G, which are the propagate and generate bits, and the initial carry-in. So go back a little bit. Each carry-in is G sub I, P sub I times C sub I sub I minus 1, where this is the carry. And this thing is like, this is the recurrence. So you can express this in terms of just all the way down. Okay, so for C sub 0 is the base case, and that's just G0, P0, and C minus 1. And you have those all up front, because C minus 1 is just always set to 0. And so you can plug that into this expression for CI. CI is GI, PI, C0. But we have an expression for C0 with stuff that we already have. So we just plug that in and we get this thing. And then you unwind it all the way down. And then so it may be a long expression, but it is all expressed in stuff that you already have and can do in parallel. And so you can, these are associative operators. And so you can compute all of these with parallel scan. And it turns out you can also express it with Boolean matrix multiplication by setting the matrix to this, but actually I just think of it like this in terms of unwinding the expression. And this is called carry look-ahead addition, and it turns out that pretty much like every computer uses it. They just make circuits to implement this logic. Yeah. So this idea goes back to the 1800s. They didn't have an implementation of it, but they had this idea that it would be an issue if you had to serialize the additions. Okay. Everyone got it? Does that make sense? Okay. Another, I guess, so this one is lexical analysis, and this one is different from the other ones in that it doesn't use bits or numbers, but it is still another way that you can use parallel prefix on things that are not just arbitrary things that you apply functions on. Lexical analysis is this operator that you have a long string of characters and you want to cut it up into tokens. Tokens are like, you can think of it in your compiler, like tokens are just, in your compiler, it'd be breaking it up on the white space and on special characters like comma, parens, and so on. And this is like the first step that your compiler does always, to cut up your program into pieces, and then it tries to understand what you're doing. And yeah, so suppose that we have some regular language, which is something that you are going to use to, something that the compiler uses to understand the programs. And we can represent it with an automaton that starts in some state, and based on what characters you read, then it transitions between the states based on what character, yeah, it transitions between the states based on what characters you've read. And this is how like programming languages work. Like you start in some initial state, and then based on the lines of code, then you can move into different states. Or yeah, based on the lines of code and based on the characters in the lines of code. You can move to different states, and you can say like which ones are operators and so on. So if you have to read this, the initial way that you would do it is you can just read character by character. And then eventually you would end up in the correct state. But again, this is serialized. So you want to do this faster because then it would take you a super long time to compile. And the goal is to do it in parallel. And yeah, basically the high level way that it works is that you replace every character in the string with the array representation of the state-to-state function, which is the column. So you think of every character, not just as a character, but as a way to go between states in some sense. And so you can think about like now basically your operation is going left to right, and you're starting from some state, and you use each character as the transition between states. And the transition is associative because you can kind of think about it and think, or yeah, you can think about it, and then the composition of two character states is they are composable and they are associative.
How would you, maybe I'm not thinking about this part, but how would you like, they're associative, sure, but like, how would you know the state of like you have a state and you see this new character, and so that goes to the next state, but like, if you haven't, I guess you haven't computed like what the state is at that point yet.
Mm-hmm. Yeah.
Like what are you calculating?
Yeah, it's a good question. So like, yeah, so like I said, like you have one character, you're in state X, you read the character, maybe you go to state Y. And then you have two characters, like you started, it's similar to carry look ahead. Like you're trying to decompose this into things that you already have up front. Like if you had the composition of your entire string, you know your starting state, and you just have made a state-to-state function. And if you've composed the entire thing, you would compose from beginning to end.
Okay.
Does that make sense?
I think I get the idea.
Yeah, like basically, yeah, like the problem is that at each arbitrary point in the string, like if you just started somewhere, you don't know what the state is at that time, but you only need the state, you know the state at the beginning. And so if you had a function that just told you what state, like the beginning and the entire string, like, sorry, you're trying to make a function that if you read the entire string and you started at that initial position, where would you get to at the end? And so you're just trying to make that intermediate function through composition. Yeah. And so you compose all the intermediate functions, and then you have the initial state, and you just index into that once you've composed all the arrays together. Okay. Another thing that we often do in sparse linear algebra is called segmented scan, which is just a variation on scan. And it takes in as input an array, and it takes a Boolean array of flags. And the flags basically tell you where to reset your scan. So normally you would just go left to right the entire way. Here we go left to right, but if we see one, we reset using this as the initial element. And And so here, like 1 and 2, you see 1 and 3, but now instead of 6, you just reset at 3, and so on. And the way that you think about this in sparse linear algebra is that each one of these is like a row. And then so you can do some segmented scan on the rows, and then you try to use those intermediate results in your answer.
Yeah, and specifically with sparse, it might be helpful because, or why would it be specifically helpful in sparse?
Yeah, we'll spend at least one lecture later talking about sparse representations, but the way to think of it is like normally when you have a matrix, you have like an adjacency matrix. When it's sparse, almost all of those entries are 0.
Yeah.
And so it's more efficient to just write the column IDs directly with the values.
Oh, okay.
Yeah. So that's like the column IDs, you would have like a separate array up here with the column IDs, and these are like the values. If you actually had a sparse matrix. Yes, but we'll talk a lot about sparse representation. Another thing with parallel prefix, everything else was in 1 dimension, pretty much. I guess arrays, I guess the lexical analysis was still 1 dimension, but just vertical rather than horizontal. You can do parallel prefix in any arbitrary dimension for any arbitrary tensor, but here is for matrices. In image processing, they often compute things called summed area table, which is, and the summed area table is this algorithm or data structure that allows you to query the sum of elements in an arbitrary rectangular grid on, like you have a 2D grid as your input, and you want to query the sum of any arbitrary things, any arbitrary rectangles, and this is often used for like pixels, for example. Yeah, so the way to do this is that you compute prefix sums along both dimensions. You compute both in the X and the Y dimension, horizontal, this is horizontal, this is vertical. And so each element, once you do both horizontal and vertical, is the sum of all elements in the rectangle cornered, starting from the initial position, like starting from upper left, and then going to the position that you are currently in. Okay, so this gets us, so naively, this allows you to get arbitrary rectangles, but only starting from here. And so how do we use that to get arbitrary rectangles? Basically use inclusion exclusion on the points. So yeah, so this is like, for example, the rectangle that we want. And this one would get us all these elements. If we subtracted out this, that would give us this, like this one. And then if we subtracted out this, that would give us this, but has subtracted this out twice. So now you just need to add that back in. But you have all those values, like these are the corners that give you those elements of those rectangles that you're trying to add and subtract in. So in 2 dimensions with 4 additions and subtractions, here, yeah, you just add in the one that you subtracted out twice by accident, and then you subtract out the left and the top, and then you get the rectangle. And you can compute those corners in like constant time. And it turns out that you can do this in arbitrary dimensions also. It takes 2 to the D, where D is the number of dimensions you have. Because with inclusion exclusion. Yeah. You notice that this requires you to have an inverse, which is true for some, but is not true for arbitrary operators. Yes, I do want to talk about it. So another application, more complicated than the previous ones, is called tensor region sums. And in a lot of scientific computing applications, you may want to compute potentially overlapping regions of a tensor and you want to reduce them into some single region. So in summed area table, like we just saw, basically you want to compute arbitrary rectangles. In the fast multipole method, you want to do the opposite. You like define some area, and then you want to reduce everything outside the area into one single scalar. Yeah. Yeah. So to be more precise about it, the excluded sums problem underlies some applications that require reducing regions of a tensor into a single value using some arbitrary operator, arbitrary associative operator. And in 2D, it takes this n by n, n1 by n2 matrix and a box size k1 by k2. And this is different from summed area table, because in summed area table, you can query arbitrary box sizes. But in this one, you have to fix the box size up front. But yeah, you fix the box size up front, but you may do inclusion and exclusion in this problem. And you want to compute every single exclusion from every single box, given a fixed box size. So the element in this position, x1, x2, after you run the algorithm, would be the sum of all the elements outside of it. Outside the box, like with the upper left at x1, x2, and the x and y as k1 and k2. Okay. And the included sum is just the reverse problem. So the input is the same, but instead now you want to compute the sum of elements inside the box rather than outside. And you can clearly compute all of them in n1, n2, k2, k2 time, k1, k2 time, because you have n1, n2 points, and each box takes k1, k2 to compute. Can you do it more efficiently? Yeah, I'll tell you how to do it. This is an example. So this is your input matrix here, and suppose this is your box. And for inclusion, 5 plus 3 plus 2 is 10. And for exclusion, it is 81. But the thing to notice is that you computed all of the values, not just one. And you want to be able to query them in constant time. If you had an inverse, you can clearly convert between the problems. Like if you have an algorithm for this inclusion problem, you can clearly convert it into an algorithm for exclusion just by doing subtraction. Like you can easily compute the total, and then you subtract out the query points, and then you can get this, which works if you have an inverse, but may not work in arbitrary cases. So we can think of two versions of the problem, weak and strong, where weak requires an operator inverse and strong does not. And clearly any problem that can solve the strong version can solve the weak one also. This will relate to parallel prefix. So yeah, so these are some bounds for the problem. You can use the summed area table. Like I said, you can do it in arbitrary dimensions, and that takes 2 to the d times n time. It takes space theta n. There's another algorithm for the excluded version of this problem. It also takes, actually it takes omega 2 to the d to the n. And I was working on this, and we come up with algorithms that can do it in d times n, where d is the number of dimensions. This is some experimental results. It does I'm coming back around. It will go to prefix eventually. But the reason that we're doing this is that we want to do it in higher dimensions. And the previous algorithms have exponential dependence on the dimension. So this is a summed area table algorithm if you have subtraction. And because it has exponential dependence on the dimension, it goes faster up into the right. Up into the right is bad because this is in time. And yeah, these are the two new algorithms, and these are lower as the dimension gets higher. Okay, we are back at prefix. So first, for ease, we can try to solve it in one dimension. So in one dimension, this is just saying you have an array and you want to compute, for every point in the array, you want to compute the sum of like the next k things into that point. So this is your input. And the way you do this is through prefix and suffix sums. And prefix is what we were just talking about, just scan from the left. Suffix sum is the inverse, you scan from the right instead. And you can use very similar algorithms for both prefix and suffix, and they all follow the same bounds. And the problem in one dimension is, yeah, you want to output another list, A prime, of the sum in K. And so basically you have K up front, which is important. And the way this works is that you basically cut up your array into pieces of size K, and you do a prefix on your chunks of size K, and you do a suffix on the chunks of size K. And this is like the picture that tells you kind of how it works. Like you have prefix, which is going up this way, and you have suffix, which is going out that way. And any arbitrary point, like for example, this is your window, you can express it as the sum of one prefix and one suffix. And that is linear time, because it takes linear time to pre-compute these, and then each one, you can compute this n thing in parallel by just like summing up two things. Yeah, so this solves it in one dimension. And you basically, to do it in arbitrary dimensions for the included problem, you just do it along each dimension. So yeah, so like in 2 dimensions, first you do it horizontal. It doesn't matter what order you do them in. First you would do it horizontal, and that would give you, each row is like decomposed into k-size windows, where the k-size windows are horizontal. And then if you do the same algorithm vertically on that previous result, now each one is, if you sum up this k window is now all of these together. And it's 1 pass per dimension, so that's where the d times n comes from. Yeah, so if you had inverse, it would be done. If you don't have inverse, you can use a similar trick, basically by doing dimension reduction. And the way that works is in 2 dimensions, basically, if you're trying to exclude this part, you decompose the region into 4 parts. These 2, which are things outside the range in either x or y. And these things are outside the range in just x, but not y. And these things may be outside the range in either x or y, but can be inside, like, they're inside the range here, but they're outside the range in this dimension. Yeah, so you decompose this into 4 parts. And the way you compute the 4 parts is using that same prefix-based algorithm that we were doing before. So you do yeah, you do horizontal prefix the entire way, and then you do vertical like window prefix sums that way. And then you can do that computes you this region. And if you want to compute this region, then you do suffix sums horizontally, and you do the vertical ky prefix. And then you want to compute the other side. So you already have solved the prefix and the suffix on that side, so you can just use the same result. You just do prefix and suffix on that S-grade. And that will give you this region and that region. Yeah, and it turns out that you can do it in higher dimensions through a similar trick. This is 3 dimensions. Illustrating higher than 3 dimensions is hard. But yeah, so you do dimension reduction, but now this is in 3 dimensions, so you, yeah, so you do it like in this side, then at this side, then overall like on those partitions. The total time is d times n, because it takes 1 pass through the entire thing in each dimension, and the space is theta n. That makes sense? That was a lot. Actually, you don't need to do parallel prefix for that, I guess, because each of the, you're trying to do like prefix on just small windows. And so you can parallelize over the windows because those are independent. But I guess if k was large, you'd use parallel prefix. So this last part is short. We'll talk a little bit about how you map data parallel algorithms onto actual hardware. So in history, there used to be a machine called the connection machine. The first one was like CM1, and then they had CM2 and so on. And these were based on SIMD design. So they had a lot, like 65K, 64K, depending on how you define K, of 1-bit processors. And each one of them had 4K memory. So you had a huge number of tiny processors. And so you had to express all your algorithms in the SIMD paradigm, and they were connected with some network format that I'll talk about networks in like a future lecture in much more detail. And you can, in CM2, you can now add floating point numbers, but just one floating point numbers. And they were programmed in a data parallel way using Lisp and C. And in CM5, they introduced vector lanes. So these days, pretty much in all modern machines, we have things called vector registers. And so normally in registers, you can only load one scalar, like 32 bits or 64 bits, but vector registers are way wider, like 256 or 512 bits. And so you can load a lot more elements, but you are restricted. You have to do the same operation on all the elements. And so you just load a whole bunch of them into the vector register. You have like 2 vector registers and you just add them. And the elements, like the elements one by one, they're called vector lanes. So you have lanes inside the register, and the lanes are like number of bits in the total vector register divided by the number of bits per element. So that's like 8. So you would say like 4 lanes or 8 lanes. Yeah, and for GPUs, for n-way parallelism, a GPU can use n threads divided into thread blocks, and it maps those threads to ALUs and blocks onto streaming multiprocessors in GPUs, and that is done by the compiler. You have these thread blocks with a huge number of threads, and then those get mapped to the actual computation. So to wrap up, data parallel algorithms apply the same operation to multiple data simultaneously. So it's SIMD, single instruction, multiple data. Basically like a huge fraction of data parallel algorithms are prefix sums in their applications. And one thing that I think is cool about them is that often they look serial, but if you kind of like try to decompose it into a different way, usually often by unwinding their recursion, you can find surprisingly parallel solutions, even though it looks like it has a chain of dependencies. And you can implement those algorithms. Of course, you can just implement them normally, like through threads, but you implement them explicitly with vectors in CPU, and it's the main programming model in GPUs is through data parallelism. That's it. Thank you.
I feel like